Hello everyone. In this video we're going to be talking about the fundamental theorem or theorems of calculus. So you know that if someone says something's fundamental, it's a big boy. It's important. And it is. So historically, calculus was broken up into two different parts. There was differential calculus, which was developed by Newton and Leibniz independently of each other. And they both got different treats named after them. So Newton obviously got the Fig Newton named after him, and Leibniz got a cookie that's covered in chocolate called the Choco Leibniz named after him. So if you do something really good in calculus, you'll get a cookie named after you. And then there was integral calculus. Integral. And it was developed by a ton of people. But namely the two big guys in this were Cauchy and Riemann. And for a long time, these two were separate things, and never the twain shall meet, until the fundamental theorem came along. And the fundamental theorem broke apart these walls and connected the two. So, what is the fundamental theorem of calculus? So there's two parts to it. So, fundamental theorem of calculus part 1, and these are, some books say part 1 is part 2, and some books say part 2 is part 1. It doesn't really matter. I'm going to use a specific one for part 1, and I'm going to use it to show you how part 2 works out. So the first fundamental theorem of calculus says that the definite integral from a to b of a function is equal to big F of b minus big F of a, where big F prime of x is equal to little f of x. So right here we see a relationship between an integral and its derivative. And this is the first fundamental theorem of calculus. Some books say it's the second fundamental theorem of calculus. It really doesn't matter. And the second fundamental theorem of calculus, which is called the first fundamental theorem of calculus in some books, is that if I take the derivative of the integral from any number to x of f of t dt, that's just equal to f of x. So again, we see this relationship between a derivative and its integral. Proving the first fundamental theorem of calculus is kind of a pain, and we won't really talk about it in this course. Maybe one day I'll upload a video where I prove it. But the second one is really easy using the first part. So let's look at that. So why 2? And if we use the first fundamental theorem of calculus, we see that ddx of the integral from a to x of f of t dt, this is equal to the derivative of big F of x minus big F of a, where f prime of x is equal to little f of x. So what we have here is this is equal to the derivative of big F of x minus the derivative of big F of a. And kind of relating back to the Leibniz and Newton thing, this notation with the prime is the Newtonian notation. Originally, Newton dealt with physics things. So he dealt with a particle, x of t. And when he was looking at the velocity, he'd say x dot of t to denote the time derivative, which is still used in a lot of physics and engineering applications. And over time, this x dot ended up giving us the f prime of x that we all know and use. So that's just a side tangent there. This Ddx notation is attributed to Leibniz. And his notation in general was df dx. So we're taking a small change in f. So delta f, think of our slope, right? So slope is delta y over delta x. But what is y other than f of x? So it's delta f over delta x. And then we take the limit as delta x goes to 0, and the deltas become d's. And that's where we get the Leibniz notation of a derivative. So that's a short historical side note. If you're interested, you can go ahead and comment. I can recommend some good history of math books for you, but there are a ton online with respect to the history of calculus. Okay, so let's get back to explaining why 2 works. So f of a, f is a function and a is just a number. So this derivative is going to go to 0. And by this guy right here, that's the same as this. So this is a little f of x minus 0, or just little f of x. And that's why 2 works. So these are the 2 big things, literally fundamental, regarding calculus. It relates derivatives and integrals, and now we can kind of see a relationship between those 2. So 1 is a main focus, so we're going to work with 2 a little bit and kind of get it out of the way. So we're going to be looking at Ftc part 2, which says that the derivative from a to x of f of t dt is equal to f of x. Okay. So we'll look at a simple example, and then we can get a little bit more complicated by kind of understanding what's going on with what's inside here. So if I were to look at the derivative of this integral from 2 to x of something really complicated, we might not even be able to integrate it. We can look at e to the sine of t squared minus 4t dt. What's the antiderivative of this? I don't know. I don't care, because I can just use the fundamental theorem of calculus. And it's essentially saying that everywhere I see a t, I can just replace it with x. So this is e to the sine of x squared minus 4x, and that's it. Okay, so now let's look at a little bit more complicated of an example. And we'll look at the integral from 2. Remember, it doesn't really matter what number we put down here. 2 to x squared of, let's say f of t is going to be t squared minus 1. Or I don't want to confuse the squareds, so let's make this t cubed minus 1 dt. So this one we can actually integrate using the first fundamental theorem of calculus, and then go ahead and take its derivative. And let's go ahead and do that real quick, and we're gonna see how it kind of relates to what we're about to do. So this guy is going to be the derivative of t to the fourth over 4 minus t. And we're evaluating it from 2 to x squared. So wherever we see a t, we're going to plug in x squared. This guy is the derivative of, well, this is going to be x to the 8th over 4 minus x squared. And when we take its derivative, we're going to have minus 2x, and this is going to be 8x to the 7th over 4, so this is 2x to the 7th. Okay, now we can look at something here. This has a common factor of 2, and we also have a common factor of 1x. So this is the same thing as 2x times x to the 6th minus 1. And x to the 6th minus 1 is t cubed minus 1 when we plug in x squared. So something's going on relating these two things. And we'll get back to it. So if I were to think of this, I'll rewrite it down here. I'm just going to copy and paste it. Okay, we can think of like some function. Let's call it h of x. If we think of this as the integral from 2 to x of t cubed minus 1 dt, what this guy on the inside is, this is h of x squared. So we can take the derivative of h of x squared dx. Or, well, not a dx. We already kind of integrated the dx and the dt's inside the integral. And we know by the chain rule that this is h prime of x squared times the derivative of x squared, right? And what is h prime of x? Well, that's the fundamental theorem of calculus again. This is x cubed minus 1. And the derivative of x squared is 2x. So given this information, we can say that h prime of x squared is x to the 6th minus 1. And by the chain rule, this is 2x times x to the 6th minus 1, which is exactly what we have at the top of the screen. So we can get a general rule for the second fundamental theorem of calculus. So here's the general fundamental theorem of calculus, part 2. And I'm going to get rid of general because we're not at the most general yet. We can say that the derivative from a number to some function g of x of f of t dt is f of g of x times g prime of x. And this just comes from the chain rule. But we can look at some other properties of the integral and the definite integral from last video, and we can make this even better. We can generalize this even more, which is what mathematicians really like to do. We like to take a principle, and it looks really simple and really basic, but we want to see how far we can push it. And let's go ahead and see how far we can push this. Okay, so I know that if I have the integral from a to b of f of x, this is the same thing as negating b to a of f of x, right? If I switch the bounds, I negate the integral. And we're going to talk about that when we talk about the fundamental theorem of calculus part 1. But this is actually very interesting, because what if I take the derivative instead of from a to a function, I look at a function to a, f of t. Okay, well, I know by this property right here that this is the same thing as the derivative of negative integral from a to g of x of f of t dt. And since it's a derivative, we can pull that constant out. So this is negative the derivative of the integral from a to g of f. And we know what this is by the fundamental theorem of calculus. So this is negative f of g of x times g prime. And this is pretty good. This is a really nice property. But we can extend it even further, because what if it's not a number? So what if we're given the derivative of f of t dt, but instead of going from a number to a function or a function to a number, we're going from a function to another function. We're going to have to be a little sneaky here. So what we're going to have to do is, if you remember from the last video, we can pick a number in between those two, and we can separate it out. So this is going to be the same thing as the derivative of the integral from g of x to some number of f of t, plus the integral from that same number to h of x of f of t. And we know what each of these are now, and we know that we can split derivatives across summation. So this is the same thing as the derivative of this guy plus the derivative of this guy. So we know that this is negative f of g times g prime plus f of h times h prime. And this is actually the most general we can get this without going too far in. So this is the most general fundamental theorem of calculus that you probably need to know for calculus in general. So the integral from g of x to h of x of f of t dt. If I take this whole thing and then take its derivative with respect to x, this is f of h of x h prime minus f of g of x g prime. And this is probably the most general fundamental theorem of calculus you can get using the tools that we currently have. So now that we've gotten all the nitty-gritty details out of the way, let's do an example with this. So let's take a look at the derivative of the integral from x squared to x cubed plus x. And we're going to look at the sine of t dt. Okay. So we could integrate this. We have a formula for integrating the sine, but we don't need it because we have the fundamental theorem. So this guy is equal to the sine of x cubed plus x times the derivative of x cubed plus x minus the sine of x squared times the derivative of x squared. And so all we have to do is evaluate the derivatives. So this is 3x squared plus 1 times the sine of x cubed plus x minus 2x sine of x squared. And that's as simple as you can get this. All right, that's it for the second fundamental theorem of calculus. Now let's look at Ftc One. Okay, and what does this say? Remember that this says the integral from a to b of f of x dx is equal to big F of b, so the top minus the bottom, where f prime of x is equal to little f of x. So big F is the it's an antiderivative of f. It doesn't need to be the general antiderivative, but it needs to be an antiderivative. So the first question is, I guess, why doesn't it need to be the plus c? And the answer is technically it is the plus c. But it's the same c for both f of b and f of a. So the integral of f of x dx, the general antiderivative, is big F of x plus some constant. And so when we look at big F of b minus big F of a, we're just going to call this big F of x. So it's actually some function, let's say g of x plus c. So when we look at this is actually g of b plus c minus g of a plus c. So we're picking one of them and we're fixing c. And when we get that, we get g of b minus g of a, because this c and this c end up canceling out. So when you find an antiderivative, you have to pick one. You can't say this is 5 and this is 7, because then it's not the same function. And that's the big principle here. Okay. So last video, I promised to show you why the integral from a to b of f of x dx is equal to negative integral from b to a of f of x dx. And this is very simple once we have the fundamental theorem of calculus, because this is f of b minus f of a. And this guy is negative f of a minus f of b. And when we distribute that negative, it becomes f of b minus f of a. And it's that simple. It's not as simple once we look at the summations and all of that. But if you were to look at it in terms of summations, you'd have, instead of b minus a over n, you'd have a minus b over n. So you'd factor out a negative from that, and you can factor out a negative from the sum. And you would see that it gives you the same answer. Okay. So now that we have the fundamental theorem of calculus and it's kind of explained, let's look at a quick example. We're going to look at the integral from, we won't use trig functions just yet, 2 to 4 of x squared plus 1 dx. So the steps with this is 1, we're just going to look at the antiderivative of f of x. And in our case, we know that x squared plus 1 has an antiderivative of 2x, 1/3 x cubed plus x plus c, but like we said before, that c doesn't matter, so let's just take it to be 0 to make our lives a lot easier. Okay, and this guy, we're going to call big F of x. Next, we're going to evaluate f of b and f of a. So in our case, f of 4 and f of 2. So f of 4 is 1/3 times 4 cubed plus 4. And f of 2 is 1/3 times 2 cubed plus 2. So 4 cubed is 64. This is 64 thirds plus 4. And the 2 cubed is 8, so this is 8 thirds plus 2. The next step is we're going to compute f of b minus f of a. So in our case, 64 thirds plus 4 minus 8 thirds plus 2. And we're just going to simplify it. So 4 minus 2 is positive 2, and 64 minus 8 is 56 over 3. So we can combine these two things to get one singular fraction. So it's 56 plus 6, or 62 thirds. And that is the value of our integral from 2 to 4 of x squared plus x dx. Okay, so a little bit more complicated of an example. We'll look at the integral from pi over 3 to pi over 2 of sine of x dx. Now, the antiderivative, so the antiderivative of sine of x is cosine of x. But it's not just cosine of x. It's negative cosine of x, because the derivative of cosine is negative sine. Okay, so next, we're going to look at negative cosine of pi over 2 and negative cosine of pi over 3. Now, negative cosine of pi over 2, if we look at the unit circle, it's right up here. And cosine is the x value, because everything is cosine, comma, sine on the unit circle. So this one's pretty easy. Cosine of pi over 2 is 0. So negative cosine of pi over 2 is 0. For pi over 3, I can never remember if it's square root of 3 over 2 or 1/2 or any of that. So I always just make a triangle. And if I call this pi over 3, this guy has to be pi over 6 to even it out. And I know that this type of triangle is a 1, 2 square root of 3 triangle. And 2 is the biggest, so 2 goes over here. And a nice property about geometry, at least planar geometry, is that the bigger side is opposite the bigger angle. So if I divide something into 3 parts, it's going to be a bigger value than if I divide something into 6 parts. So this guy is going to be bigger. And square root of 3 is bigger than 1. So this is 1. And now if I'm looking at the cosine, remember that cosine is the adjacent side over the hypotenuse. So this is 1/2. But we can't forget about that negative, so it's a negative 1/2. And then finally, we compute. So it's negative cosine of pi over 2 minus negative cosine of pi over 3, and that's just equal to 1/2. So the integral from pi over 3 to pi over 2 of sine x dx is just 1/2. Okay. So these were the big things about the fundamental theorem of calculus. It's fundamental because it relates derivatives to antiderivatives. And it's very useful in simplifying. Okay, so let's take a look at what we did previously. We saw that the integral from 2 to 4 of x squared plus 1 dx, we take its antiderivative, we plug in the upper bound, plug in the lower bound, and subtract the 2. And we get 62/3. But let's see how much easier this is compared to the definition. So we have this guy. It is, by definition, the sum of f of x sub I delta x. So we get delta x, b minus a over n, and x sub I is a plus I delta x. So it's 2 plus 2i over n. Now we plug in this x sub I into f. So this is going to be 2 plus 2i over n squared plus 1. We distribute it out, simplify, combine like terms, and we get 4n squared I squared plus 8 over n I plus 5. Multiply it by delta x, we get 8 over n cubed I squared plus 16 over n squared I plus 10 over n. And now we sum it up. So the sum of f of x sub I delta x is 8 over n cubed, the sum of I squared, plus 16 over n squared, the sum of I, plus 10 over n, the sum of 1. And we just use our formulas here. I squared goes here, I goes here, and 1 goes here. We can simplify and reduce a little bit more, and then taking the limit as n goes to infinity, we end up getting each of the terms added together as 8/3 plus 8 plus 10. We can combine this to 18, get a common denominator of 3, and we get the same answer. So while this is the formal definition, the fundamental theorem of calculus, as you can see, is so much easier to work with, and that's why it's such a useful and important tool in math, and in particular calculus. As always, thank you for watching. If you have any questions, put them in the comments below, and next time we will talk about the net change theorem and indefinite integrals, which is essentially just the antiderivative.